Morning, everybody. Apologize for my lab outfit, but I'm going to be on the procedure table at 11:15 today. So I'm going straight from here to getting shots in my neck. So they told me to wear comfortable clothing, so I did. Let's see. I'm not sure if we'd made it to chapter 20 yet, but that's where we're going to start. And what we need, so chapter 20 is like pretty big. I don't know if you like looked at the number of sections and stuff in chapter 20. It's pretty long. I had somebody ask me, are you going to cover everything in this chapter? My answer is like, I don't cover everything in any chapter. But like, follow the homework. Like the homework is your guide, right? If I did not assign a problem from a section, right, in the book, then you don't need to worry about that, right? So I try to pattern the exams and everything off of what you've already done in homework and that sort of thing. All right, so what we're going to do is we're going to move from voltage, right, this concept, something that's a little bit like energy but not quite, how it's related to electric field, and we're going to move and we're going to apply that and we're going to start like building circuits, right? So today we need to talk about batteries, we need to talk about current, we need to talk about resistors and where power and energy goes in an electrical system, and then we'll get to how your house works and how to save electricity costs and all of that kind of stuff. All right. So just laying down a couple, like some definitions and making sure that you're oriented, because this can trip people up and this can be kind of confusing. EMF in physics, okay? This is voltage. And you're like, well, why is there a different word for it? And that is a totally valid question. I think mostly it's kind of historical in the sense that EMF actually stands for electromotive force. So electro because it's electricity, motive because we're pushing charges around, and because they thought of voltage originally as some sort of like force that pushed things, but it didn't turn out to be that. They didn't really have energy as an idea formulated at that point. But for you guys, the practical application is anytime you see EMF, you can just substitute in the word voltage, okay? The reason that we maintain the difference, okay, is because a lot of times what's printed like on a battery, because batteries provide voltage, what's printed on the battery, like 1.5 volts for a AA battery, that's the ideal voltage, right? That's the EMF. That's, if nothing is wrong with that battery, that's the voltage it's going to put out. But the voltage tends to be what the battery actually puts out. So as a battery loses energy, loses internal energy, it will stop being able to provide 1.5 volts. Instead, it'll do 1.4, 1.3, 1.2, and finally, the battery will be so-called dead. So that's why we kind of maintain this difference between EMF and voltage. But because it's physics 2B and because you're just starting at it, we're not going to worry about these sort of non-ideal batteries. You'll see me and your book and the internet and all that kind of stuff. The symbol for EMF is like this curly E, right? Kind of like that, like a script E. And we use delta V or V to talk about voltage. What's really going on here, before we get to kind of what's really going on in batteries, let's define current real quick, okay? Current, symbol capital I, is an amount of charge that flows through a conductor in a certain amount of time. And the units here are charge per second, right? Like a coulomb per second, which gets a new name, the amp or ampere or ampere, depending on what side of the pond you happen to pronounce things on. So 1 amp's worth of current is 1 coulomb's worth of charge flowing through a conductor in 1 second. And in case you missed it, we're now talking about electrodynamics. So everything up to this point has been electrostatics. We put charge on an object, and then we just see what happens to the electric field and the potential. Now, with this current definition, we've involved time. And so from here on out, it's all going to be the dynamics of charge and what's going on. This gets a little bit interesting because if we let's take a wire, a conductor, right? And like a wire is cylindrical, right? Okay, there's my sort of three-dimensional wire, right? And let's say that I have charges flowing down this wire, right? Q's are going that way. That's supposed to be Q, right? Okay. And if we, usually what we say is, look, we take like a cross-sectional area of this wire, right? And we just kind of look at that cross-sectional area and we count the number of charges that flow down that wire in a certain amount of time. Well, in order for a charge to move, what does it need to experience or be in? It needs to experience a force. And what do we call the overall pattern of forces that charges are experiencing? We call it the electric field. Now, I think last time I got finished telling you that the electric field inside any charged conductor is 0, right? And that's true when it's the static case. And for our intents and purposes, everything I taught you about lightning and Faraday cages still applies because that happens so quickly that it's considered to be the static case, and that's how nature works. However, when you have a steady flow of charge down a wire, like if I've got charge flowing up that direction, that means my electric field has to be inside the wire and along the wire. Well, we know that electric field and potentials are related, right? So in order for charges to be pushed along a wire, they have to be an electric field. And in order for the electric field to be there, that means there must be a potential difference across that wire. So in order for charge to flow, we need voltage, and voltage will be provided by the battery. So in electrodynamics, right, when charges are being forced to move places, you do have electric fields inside of conductors. Just kind of by definition in the way that nature works. All right, let me kind of try to outline here, okay, or at least visually represent what's going on with like batteries and dead batteries and things like that. Let's see if I can get this to work. This video is going to show you, and I think I'm just going to narrate because the sound tends to kind of drop out as I play these. But you can see here that we've got like 2 sets of batteries. So there's batteries here on the left and there's batteries here on the right. And we've got 2 different multimeters that are telling us the voltage that are across these batteries. If I remember correctly, the batteries on the right-hand side are dead, okay? And I want you to take a look as they go and they're hooked up to light bulbs. So these are loads, right? These are things that want to take energy from the batteries and do stuff. In the case of a light bulb, light up, right? So let's see, okay, kind of what happens here, right, as they do this demonstration. So you can see here that both batteries show voltage, right? When there's no load across them, both batteries are just fine. Here on the left, you connect the light and the voltage hardly changes. Those are fresh batteries ready to go. Over here, okay, when they turn it on, no light, and do you see how the voltage drops to 0? Okay? So this is kind of what we're talking about when we're talking about the difference between EMF and voltage, right? The EMF of both of those batteries was the same. It looked like they were about 5 volt, 4.5 volt, right? EMF, meaning that when there's no load, they're not hooked up to a circuit, that's the potential the battery wants to provide. However, when you hook them up and you actually ask the battery to start pushing charges around the circuit, the dead battery is the one that its voltage drops to 0, right? The good battery, the EMF and the voltage are about the same. On a chemical level, what's going on inside the battery is the chemistry is altering. and the battery's internal chemistry is fighting against itself. So a dead battery hasn't run out of EMF. What it's happened is all of its energy is being like used up internally inside the battery's chemical reactions. Okay, there's no free charges to be able to push out from those chemical reactions into the rest of the circuit. So a dead battery still might have the same EMF as a good battery. It's just the dead battery, the chemistry has gotten to the point where the voltage coming out of that battery isn't the same. So that's why we kind of maintain the difference, as it were, between those two things. All right, so this takes us in the direction of talking about where electrical energy is going when we hook things like batteries and charges and we start trying to get those charges to do work for us, okay? And so it would be nice, right, to have some sort of relationship between voltage and current, okay? So what do you think? Is this like a direct relationship, like the more voltage in a battery or in a circuit, the more current you get? Or is it inversely related? Like more voltage means less current. What's your sort of intuition there? What do you know? Direct or inverse? Good morning, everybody. You awake out there? What happens if I say do like 5 volts across the wire versus like 120 volts a wire? You're going to get more or less charge moving down that wire? Probably more. Good guess. Same. Like in physics, you've been burned before, right? No, but in this case, it's not the same, right? In this case, the higher the voltage, the higher the current. But voltage and current are not equal to each other, right? The different units, one's potential, one's amps, or one's voltage, one's amps. So there is a constant of proportionality, okay, that we introduce, okay, called the resistance, that helps relate these two things together. Now, resistance, like what does that sound like? What back in 2A, when you had resistance to movement, what did we call it? Friction, right? Okay, it was friction. Whenever friction was involved, life got worse because there was more stuff to keep track of, right? Okay, same thing's going on here. It does. And without friction, you wouldn't be able to walk anywhere, right? So, I mean, it's a useful thing. And the same thing goes for resistance. It's going to cause a little bit more difficulty, but like we need it to be able to talk about how electric potential and current work together to deliver electrical energy to whatever device we want to power. So think of it as electrical friction, right? We call it resistance because it resists the flow of electrical energy through a circuit. When you take like any friction, right, and like you rub your hands together, say, okay, where does the energy go that like friction is taking away? Transfers it into heat, doesn't it? Okay, that's what electrical resistance does too, right? So it takes energy away. So battery gives some charges some energy. The electrical resistance in the circuit will take that energy, okay, and turn it into mostly heat, okay, and maybe some other things. But that resistance, right, is like friction from 2A. It's just like the electrical analog to it. We call the thing in the box Ohm's law. George Friedrich Ohm, okay, is who we kind of credit with putting all this together and developing a lot of the information about resistance. The unit for resistance is ohms, and the symbol is the Greek letter omega. So what do we got here? We got potential has units of what? Volts, right? Current has units of amps, right? And then resistance has units of ohms, right? With the symbol V, symbol A for the unit, and then ohms, right, is symbol omega. So what's an ohm? Well, it looks like it's a volt per amp, doesn't it? Yeah, that's pretty much what it is. I've given this advice before, but I think it really starts to stick right now. Give up on units. I know that sounds weird coming from a physicist, right, or a scientist, right? But honestly, like when I say that, I don't mean like stop using them. I mean give up on trying to like figure out what units equal other units. SI units, like the metric system of units, is like hard coded in all of our math and mathematical models and equations to work out. All of our equations are already dimensionally consistent. And so as long as you use the standard unit, like for current, if you're given a number in like milliamps, what should you do to that number before you put it into an equation? Convert it to amps, right? If you're given microcoulombs, you convert it to coulombs. If you use the standard unit for all of these things, you are guaranteed to get the correct unit out for the thing that you are solving for, assuming you've done your algebra correctly, okay? So that's what I mean by kind of give up on the units, right? You can keep them in line and see if everything cancels and all that kind of stuff, but you're big boys and girls now, right? You've done 2A, okay? And if you really want to dive deep into the units, you'll go down a rabbit hole, okay, that is not worth spending any time on. Okay, let's, yeah.
When I was doing the homework, I learned that voltage over meter, or V over M, is equal to newtons over coulomb.
Yes, true.
Yeah, how they relate it. I mean, that's what the homework said.
I know. No, and they're not wrong, okay? Because a volt per meter, let's do this up here. So it turns out, okay, that a volt per meter and a newton per coulomb are the same. Does anybody remember where newton per coulomb came from? Like what is this unit, newton per coulomb? It's electric field, okay? Because the electric field is force divided by charge, okay? So where's the volt per meter come from? Well, electric field is also potential times distance in a capacitor. What's this? Volts. That's a distance, it's not a second, so that's a meter, okay? And I did that wrong. Okay, there we go. Now it works, right? But so you can end up, right, with these are equivalent units. But to like figure that out, you really got to break down what a volt is, joule per blah, 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 joule per coulomb, and then the newton is a kilogram meter per second squared. Like you could really kind of go deep in here, right? But it's not worth doing that, right? You can just say, oh, these are both electric field units, right? It just kind of depends on, am I talking about like capacitors or am I talking about Coulomb's law? So yeah, I get you. It can be confusing, right? And you're like, well, but Mr. Basil, this is it. Yes, it's true, but they're both all of those are SI units, aren't they? A volt, a meter, a newton, those are all the standard units. That's kind of what I meant, right? You're going to get the thing that you're looking for. And for me, I look at this and I go, it's the same thing. Wiley Plus goes, no, it's wrong, right? I know, there's limitations to the online stuff, right? So, no, thank you for pointing that out because sometimes we physicists play fast and loose with our units. As a matter of fact, in certain places, we will redefine our numbers and units so that all of our units are dimensionally gone, like they're all equal to 1, so that we no longer have to keep track of the units. We're really squirrely that way. It drives the engineers and mathematicians up the wall. All right, let's see what happens with thinking about like kind of what resistance is doing in an electrical circuit here. Okay, So I like this animation because
To make a
you see the
current
battery
flow
over
through a
there,
conducting
and then that
material.
symbol right there is a resistor. And do you see how the battery
A
kind of looks
voltage
like a
is
set
needed.
of like an escalator or
The
something?
current is always
Okay.
proportional
And
to the
charge gets
voltage.
pushed up the battery, okay?
The constant
And then the charge comes
proportionality
around and
is
falls
called the
down the
resistance.
resistor, like a
This
waterfall or a
equation is
set of
known as
stairs or
Ohm's
something like
law.
that, okay? So you can
An
think of
element
batteries
in an electric
like
circuit with resistance
escalators or
is called
elevators.
a resistor.
Okay? They move charges to areas of higher electric potential and thus electric potential energy. And then resistors, right, will use up that electrical energy to either generate heat, say in the case of a heater, or in the case of your phone, the resistive element isn't actually a resistor, it's the processor and the screen and everything that is using electrical energy. But the point is, there's some load somewhere in the circuit where whatever energy the battery provides to the charges then deliver that energy to the circuit to be able to do something, right? So if you kind of get in your head this idea about electrical circuits, about batteries pumping things up, and then everything else in the circuit is like pulling that energy down, you'll notice conservation of energy has to hold, right? Whatever, let's say the battery gives a charge 5 volts, okay? If there's only this single resistor connected, what must the voltage drop be in the resistor? It's gotta be 5 volts. That's how we conserve the energy and conserve charge, do all those kinds of things, right? So that's what's going on there. And I should mention that we have superconducting wires in this class, right? Okay. So whenever we connect a wire between things, we always assume its resistance is 0. That's not strictly true. Like in reality, there's resistance within copper and things like that. Everybody wave to the dean. I just wanted to get more wet. Say hi. Yeah, there's our dean. She's my boss. Clap so I get more pink. So the idea here is we're going to use, right, wires that have no resistance in them. But in fact, wires do have a little bit of resistance. So
Under the influence of an electric field.
So this demonstration
Electrons move through a
is
metal,
supposedly
much as a
trying to
marble
show us
falls
like
through a viscous
the
fluid.
it's like viscosity in
If it weren't
fluids,
for
right? They're
resistance,
showing us a very
they would
viscous fluid
accelerate
here. We
freely,
could tell because
like
there's a
a
lot of
falling
resistance
body
to
in
the
a
motion
vacuum.
of that marble.
But
as
it
they
is,
switch the camera,
they move on the average at a constant speed.
Switch the camera.
Resistivity is like
You don't have to
viscosity.
watch it all the way down. Okay,
The
here we
more
go,
of it the
right?
material
Yellow,
has,
red, and blue.
the
Which of these
slower
has more
the particle will
resistance?
move through it.
Definitely the one on the left, right? Okay. So just like in a fluid, a higher viscosity leads to a slower movement of an object through that fluid. The higher the resistance of a wire or an element or anything like that, the slower the charge will move through it. And I should mention too, okay, and this is this catches some people off guard. The speed at which charges flow in wires is actually very slow. I know it feels pretty fast, right? Like if I come over here and I hit the off button, okay, that shut off pretty quick. As a matter of fact, it had a dimmer circuit in it, which lowered the voltage. Instead of just cutting it, it just turned off the voltage, right? But if I hit on, it's like instantly the lights come back on again. However, charges in wires actually move at like a speed of millimeters per second. In 1 meter of copper wire, it can take almost an hour for a charge to get from one end to the other. That's because those charges are like taking random paths and bouncing around inside of the copper atoms and all kinds of stuff that's going on. But charges move really slow through wires. It's called drift velocity. The drift velocity of an electron in a wire is, again, millimeters per second. It takes a long time to go places. And it depends a little bit on the type of material and how much voltage you're putting across it. But generally, it's really slow. So how is it that like lights go on right away? There's probably what, 30, 40 feet? So call 12 to 15 meters of wire, right, between that switch and all the lights in this room, why do the lights go on right away? Something is being transmitted very quickly through the wire. But it's not the charges. And it's not the current. It's the other one. Which one? The voltage, right? So let's back up a little bit and see if we can't make an analogy with your garden hose, right? If you have a nozzle, right, on your garden hose, right? You turn the water on at the house and you go to the end of the hose, right? And you squeeze the trigger, right? Water comes out right away, doesn't it? Okay, assuming the hose was already filled with water, right? So water comes out right away. Is the water coming out the end of the hose at that instant exactly the molecule that just left the house? No. What has to happen? It's got to move, right? So what is it that caused the water to come out right away? Pressure. It was the pressure the house is delivering to the hose that got the water to push out. So voltage in this analogy is a lot like pressure. It's like electrical pressure. It's this push, right? To try to push charges through a circuit. So what happens when the charges and the push and the pull and all that kind of stuff are kind of at odds with each other? We don't see this effect as much anymore. I really should be lecturing on thunder and lightning right now. We don't see this effect, right, as much anymore because our household circuits have gotten to the point where they compensate for these effects. But have you ever turned on like a vacuum cleaner or a hair dryer or an electric heater and seen the lights dim just a little bit? Okay, as that initial sort of I'm turning something on and the house goes, ugh, right? So that has to do with a lot of factors, but one of them is electrical resistance.
Your house lights dim
okay?
when you turn
So
on
that kind of flash, right, as power gets pulled. What they've done here is they've set up a situation. They've greatly exaggerated what's going to happen here, and they've taken all the safeties off. But what they're going to do is they're going to add electrical load. So light bulbs and heating coils and stuff like that. They're going to keep adding them. And these two wires with the pieces of paper on them are connected to all of those things. So as more and more voltage is being asked for, okay, in the circuit, eventually enough current begins to flow where the wires heat up. And if the wires heat up enough and they're in contact with flammable materials, what's going to happen? You get fire, okay? So how is it that your house doesn't burn down every time everybody tries to turn on the coffee maker and the microwave oven and the refrigerator and everything at the same time, right? Circuit breakers is the answer, okay? A circuit breaker's job is to make sure that there isn't too much current flowing in a household circuit. Your house actually consists of several different circuits. Your microwave is on a different circuit from the coffee maker, okay? And so because if you tried to run both at the same time on a wire, the current would be so high, the energy draw would be so high that a circuit breaker, your house would either burn down or the circuit breaker would trip. Okay, it detects when the current's too high for a certain situation and turns off that electricity. So, in your house, maybe you've got several people that are trying to use a hairdryer at the same time. Usually, all the bathrooms are on one circuit. So if you've got 2 or 3 hair dryers going, that overloads the circuit and the circuit pops. Okay, and you got to go reset it and do something like that. So those are safety devices that are in place to help, right, not run into a problem with circuit. Okay, so back to resistance. So we can calculate the resistance, right? If we know the voltage and the current, say in a wire, right, we can figure out its resistance. If we have a device that, your phone uses 5 volts at 2 amps of current, okay? So we can calculate the resistance, the resistive load, the amount of energy that your phone charger is taking up as it works. But resistance is also a matter of the physical parameters of a wire or a system. So specifically when we're talking about the resistance of a wire, the resistance of a device, okay? And this is specifically like a length of wire, so real wire. Hi, Thunder. So there's several things going on here. You've got length of wire, right there, okay? We've got cross-sectional area of wire right there. And then this funny P in the front, this row right there, is called the resistivity. And that's a material-dependent number. You just go look it up. You look it up for copper, look it up for aluminum, look it up for gold, whatever, and you'll get a number. But notice what happens here to the resistance of a wire as we make it longer. What happens to the resistance? Gets bigger, doesn't it? The L and the R are both upstairs on either side of the equal sign, right? So a longer wire real wire has more resistance in it. Cross-sectional area is inversely related. So that means that the bigger the wire gets, the less resistance that wire will have. So if you want to send something long distance with very little resistance, right? You have a big long L and you have an A, right? I can't help myself now. We got to talk about that. We have to talk about what the heck is going on out here, okay, right? So first of all, the water falling from the sky is called rain, right? Okay, and we've got a thunder cell that's right over there, okay, and the lightning, right, will flash and all that kind of stuff. So what is air? Is air a insulator or a conductor? It's an insulator. Okay, air is typically an insulator until it isn't. Okay, a lot of insulators have something, this is nothing to do with resistance. Insulators have something called a breakdown potential. Okay, the breakdown potential is a voltage after which, like, the voltage gets so big that the insulator can no longer stop charge from moving through it. And when you hit that breakdown potential, there's usually a sudden release of electrical energy as the insulator turns into a conductor. So in the case of our thunder and lightning here, okay, we've got this, I really want to talk about the weather. There's a patch of sky over there, okay, where there is a whole lot of air that is being pulled up, okay? And it's forming this thunder cell, right? As the air gets pulled up, right, it goes up high, and as these water droplets and dust and everything that's in the air start circulating around, they start rubbing into each other. And we know that when you rub fur on a rubber rod, what happens? You get charges, don't you? So a lot of static electricity is building up, right? We're getting charge separation. That cloud right there basically is a big Van de Graaff generator, okay? And it's starting to separate out the positive and negative charges. It doesn't matter which one's which. Let's just say the cloud has negative and the ground has positive, okay? It's separating out. And now when you have, say, positive charge at the ground and negative charge up in the clouds, okay? What do you now have between the cloud and the ground? You have potential, don't you? You got high potential at the ground, you got low potential up in the clouds, okay? And that continues to kind of separate out as the air keeps moving and the rain keeps falling. And wow, it's really raining out there. This is. I'm really glad we didn't go on a field trip, right? So yeah, that thunder cell is going to come right over the top of us. So as we keep separating out those charges and the Van de Graaff keeps building up that potential difference, eventually, okay, so now we've got a bunch of positive charge in the ground. We've got a bunch of negative charge up in the clouds, right? We have a potential difference. What else do we have? If there's voltage difference, there's also what? You did it yesterday in lab. Field, right? There's electric field, right? In this case, the electric field. Now this can be reversed. I don't know, okay? But now we have electric field, right? And there are going to be forces involved there, right? Okay, forces on charges, that kind of stuff. But eventually, like I said, when the voltage difference between the cloud and the ground gets to the point where air, normally being a insulator, turns into a conductor. Now, instead of having an insulator here keeping all these charges apart, we've just, boom, turned air into a conductor. What happens? Lightning, right? Lightning is the cloud and the ground agreeing that they want to be at the same voltage, right? We literally connected the clouds to the ground, okay, and caused that lightning bolt to happen. So now charge is moving, right, between the cloud and the ground. Apparently I drew the electron current there because I did it the wrong way. So charge is moving between the ground and the clouds. So now not only do we have voltage and field, but we have flow of charge, which is current. Okay? And so lightning, thunder, lightning, thunder's the sound. It's the sonic boom, okay, as that gets emitted as the charges suddenly go boom. And there's actually, right before the lightning bolt, there is a current that is formed, right? There are individual charges moving, right, along this current pathway. And then finally, you hit the breakdown potential, and it's like all of the charges in the cloud and the ground just go boom, okay? And there's a big argument. Does lightning strike up? Does lightning strike down? The answer is yes. It totally depends, right, on where the breakdown initially happens, because there's all kinds of really crazy potential differences that are forming in between. Sometimes there's cloud-to-cloud lightning where two different clouds have different potentials, and then the lightning will arc there. There's cloud to ground, right, which is the harmful stuff to us. There's lightning. We now know in the last 10, 15 years, we've discovered that for every lightning bolt that happens from cloud to ground, there's an opposite bolt that goes from cloud to space. They're called sprites. Yeah. They're big red, and they can be 60 kilometers tall, really big. A normal lightning bolt's 2 or 3 kilometers tall. The ones that go from the top of the cloud up to space, called sprites, they're really, really big, right? So 2, 3, 4, 5. So about a mile away, okay? If you count the number of seconds between the flash and the sound, okay, and divide by 5, you get an idea for basically how far away that thunder cell is. Right now? If you walked, you'd have a shower. So anybody need a shower? I'm not allowed to take one for 12 hours. You have to walk? It's hard. I think this cell is moving that way. Sorry, we've gotten very distracted at this point, but that's all right. Where's us? We're down here. Okay, so they're saying they don't even have. Yeah, this is behind the times here, right? Okay. Okay, here we go. This is better. Okay, so here we are, and we can see kind of the color coding. This thing is sitting right over the top of us right now. Let's see how fast it's moving. Okay, so there's 10 minutes, 10 minutes, 10 minutes. Okay, so this thing developed over the course of 10, 15 minutes. So I think as long as I talk long enough today, you guys will be safe. Yeah. Okay, so yeah, 3 seconds, right? So that's pretty much right on top of us at this point. Applied physics, isn't it great? Who wanted to learn? Okay, yeah, so the cell is sitting right there because I can see the edges of it there. I can see the edge of it there. Run, Forrest, run! Oh. Make fun of them. It's probably pretty miserable out there right now. I did grab my, I grabbed my raincoat. All right, let's do more boring things like quizzes. Oh wait, before we do it, no, I did that already. I did that. Yes, there we go, quizzes. Let's do a quiz. This is probably going to be really like, when you've got resistance and a hot dog and wires, there's only one thing that can happen.
We'll skewer
So those are
this
two
hot dog
nails,
onto two
and they take a
nails
hot dog
run
and
a
they put it on the
current through
nails,
it to
and the
show
nails are
heating
just connected to the
produced by
wall.
current.
Okay, they're going to turn the switch on.
110 volts are applied to the
So
nails.
can a
and the
hot
current
dog be
begins
a
to flow
wire?
through the hot dog.
The answer is yes. There's enough salt in the hot dog
After a
for
few
current to
minutes,
flow
the hot
through
dog
it, and as the
begins to
current
steam
flows,
from the
it
heat
heats up
produced by the current.
and cooks the hot dog. Right? Slow electrocution of hot dog. I think there's a fundraiser in this somewhere. Science and Engineering Club? Right? Sell hot dogs via electrocution? No? Okay. And if you're going to do it to a hot dog, you might as well do it to a pickle.
We'll use this pickle and two nails to show an unusual
Now,
type
what do
of
pickles have in
electrical
them?
discharge.
A lot of
The
salt
nails are inserted in the
and
ends of the
some
pickle,
other stuff. And so
electrical
with the
leads are
pickle, it's really
connected
kind of
to the
funny
nails.
because you get a special
When you put
electrical
a high voltage
discharge.
across
Watch
the
it.
nails, the
I think it's
pickle
on this
lights
end.
up at
Oh
one
no,
end.
that end right there. Do you see the arcing that takes place? Right? Okay. It's kind of forms a little plasma and arcs across there. Don't leave a pickle on two nails plugged into the wall for very long. That's a bad day. And before we get into electrical power, I do need to show you something else. What is this? It's the Greek letter omega, but like what unit is it? It's the ohm, right? Okay. What's this? It's an ohm away from ohm. What's that? It's an ohm meter. An ohm meter. An ohm meter. Ohm. Ohm on the range. It's an ohm on the range. What's a range? It's a combination oven and stovetop. Drawing was okay. It's like one of the best drawings I ever do. Okay, dad jokes over. Let's talk about electrical power. Power is something you did in 2A. Don't panic. I'll help you out, right? Does anybody remember the units of what power was and what its units were? It was watts, which seemed funny in 2A, didn't it? Because watts is like electricity, isn't it? So we're finally bringing that here, okay? Symbol P for power, capital P, right? And in 2A, and this is still true for 2B, nothing's changed here, right? It's work per time, which is like work and energy share the same unit, so it's basically the same idea. What are the units of energy? Joules, and so work is joules, right, per second, and we called this, right, a watt. And we're like I said, we're used to watts when it comes to electricity. We're not used to watts when it comes to, say, like car engines or something like that. So let's do the electrical version of this. Okay, Let me make sure I get it the same way your book does, which I failed to write down. That's okay. Power in the electrical sense is current times voltage. That's supposed to be a V, by the way, voltage. And so, okay, so what are the units of current? Amps. What are the units of volts? Volts. That was a trick question. What's an amp times a volt? What's a, this is an amp, right? That's a volt. It's watts. I told you to give up on the units, right? Right? So how do you make sure to get watts out of anything? Make sure that the current goes in as amps, right? Even if you're told milliamps, convert it to amps, right? If you're told megavolts, put it in volt, right? And then you're guaranteed to get it out in watts, okay? So, right, this is a watt. It's an amp times a volt, which also happens to be a joule per second because all of these things are all the same. Okay? So you can do an amp times a volt, joule times a second. Let's make it weirder. Voltage is equal to current times resistance, isn't it? That's Ohm's law, the relationship between voltage and current and resistance. So if I substitute the voltage in, I grab this and I just chuck it in there, what do I end up with? I squared R, right? So that's another way to do electrical power. If you don't know the voltage, but you do know your resistance, right? Or we can solve it for current, which would be V over R. And I can substitute into the current instead and get what? V squared over R. So those, everything in a box there, right, is equivalent. Just different ways of getting watts. Okay, we know a watt is an energy per time, like a joule per second. So if I have a 100 watt light bulb, how many joules per second of energy is being used by that light bulb? 100, okay? It's 100 joules every second is being used by a light bulb. So that would be like a standard like incandescent light bulb, which you can't really find anymore, right? One of those old-timey filament light bulbs, right? So instead, you can buy like an LED light bulb now that gives the same amount of light, but only uses 10 watts of electrical power. So how many joules per second are going through a 10-watt bulb? 10 joules per second. How much more efficient is the LED light bulb compared to the old-timey light bulb? 10 times, right? It's 10 times more efficient. And that efficiency means we're getting the same amount of light out for a tenth of the amount of electricity that we have to put in, right? So what that tells you is just like how much better quantum mechanics is compared to classical physics, because an old-timey light bulb is using the resistance of a wire in that light bulb to generate the light, which also generates a lot of heat. And in the case of an LED light bulb, it uses quantum mechanics, which we'll get to when we finally get to modern physics, okay? So efficiency can be a little bit squirrely. Now, electrical power being measured in watts cuts home a little bit harder because we have to pay for it. PG&E, SoCal Edison, right? These power companies, right? They charge us for electrical power. So what do they charge us for? Does anybody just like read their electric bill for fun like me? Well, okay, we'll get into the other things here in a second. But like when you get down to it, what are you paying for? It's a kilowatt hour. Okay, this is interesting, right? A kilowatt. Now, just to be careful here, let me be really careful. It's a kilowatt, small k, big W, okay? which kilowatt means 1,000 watts, okay? Times an hour. That's what a kilowatt hour is. It's not per. It's not kilowatt per hour. It's a kilowatt times an hour. And what is a power times a time? It's work or energy. So PG&E, SoCal Edison, they are energy companies because they're charging you for energy. A kilowatt times an hour is a unit of energy, just kind of in weird-ish units, right? Not standard SI units, which drives me up the wall, okay? Because it should be a watt second, but then you'd have a bill for like tens of hundreds of thousands of watt seconds and people would freak out, right? Okay. So how do you get a kilowatt hours worth of electrical energy, say out of a 100 watt bulb? So 100 watt bulb, how many kilowatts is a 100 watt bulb? You're either good at moving periods around or, right, if I have 100 watts, right, and there are 1,000 watts in 1 kilowatt, divide by 1,000, what is this? 0.1 kilowatts, right? So 100 watt light bulb has an electrical power of 0.1 kilowatts, right? If you run that light bulb for 1 hour, how many kilowatt hours of power or of energy would you use? So 0.1 kilowatts times 1 hour gives you what? 0.1 kilowatt hours, right? That's what the meter on the side of your house is doing. It takes the total amount of power that's being used by your house at any given time and then multiplying by the length of time that it's using that power. So your air conditioner typically uses about, depends on the air conditioner, but let's say 4,000 watts, right? When the air conditioner is running and providing cold air to the house, 4,000 watts, right? Well, how many kilowatts is that? It's 4 kilowatts, right? If you run your air conditioner for an hour, 4 kilowatt hours of electrical energy were consumed, right? And the house would keep track of that. And then they charge you per kilowatt hour. This is a very old electric bill, okay, from back in 2009 apparently, okay? And there's a lot of stuff going on here and we don't have really much that time to talk about because I talked about thunder and lightning instead, okay? But do you see how it says baseline quantity and like baseline usage up there at the top? And then there's percentages of baseline after that. So there are state like agreed upon or mandated levels of electrical energy that you can use at your house. The amount of baseline energy fluctuates for time of year, place that you live. There's a bunch of factors that go into it. But basically, it's like it's sort of a maximum amount of energy that you are, I don't know, allotted, or I'm not explaining this terribly well, but it gets into a lot of legal wrangling between the state and the power companies. What doesn't happen when you hit that baseline is your power doesn't shut off, okay? So once you exceed your baseline usage of energy, baseline usage of kilowatt hours, power companies can start charging you more. So this is a system for like big consumers having to pay more for electricity, whereas more efficient consumers pay less, right? That's sort of how the system's put together. So you can see here that my baseline quantity for this time, sometime in December, right, was 307.5 kilowatt hours, right? And as long as I was in baseline, they were only charging me 11 cents. 11.5 cents per kilowatt hour, right? And then I went into my 100 to 130%, and I used 92 at that level, right? And they charged me 13 cents per kilowatt hour at the time. But notice what happened when I exceeded the 130% level. What happened to the price per kilowatt hour? Almost doubled, didn't it? This has changed over the years. There used to be 5 tiers. I think there's 3 now. And in fact, most people now are on the system where the time of day matters. Time of use is what they call it. But the time of day, like if you're using your electricity in the heat of the day when like everybody else is, they're charging you more per kilowatt hour, okay? And so on and so forth. So there is every 5 minutes, there is an auction that takes place within a consortium of states, California, Oregon, Nevada, Arizona, I think Washington, where like the price of electricity is agreed upon. It's an auction. So like, you know, what if PG&E needs more electricity to satisfy California's demands, right? They'll be buying. And if Nevada doesn't need as much, they'll be supplying. And you know, there's this back and forth. As of, forgot to check the statistics this morning. I know this statistic was true last semester. As of 2022, California was a net exporter of electrical energy to the other states. Prior to that, we're importing. Now we're exporting, and the reason is solar. We're now generating. And I think California exceeded 100 days last year, where 100 days in a row, 100% of the state's electrical energy was provided by renewables. Solar, dams, wind, that kind of stuff. So, you know, California is kind of surging ahead. Power prices are going up, though. It's kind of a joke to think of 11.5 cents per kilowatt hour nowadays, okay? It's actually closer to 20 cents, I think, per kilowatt hour now. Does anybody know why power prices are going up? I mean, demand. We sue PG&E all the time. Why is the demand going up? We're getting more efficient, by the way. LED light bulbs, all that kind of stuff. Where's all the electricity going? Not electric cars. You might have used it to help on your homework. AI. These large language models like ChatGPT and Gemini and all that kind of stuff consume huge amounts of power. Okay, think of like a gaming PC which uses like 700 watts to just, you know, play some games, and then multiply by tens of millions, and you've got a data center, right, that can host one of these models, right? There's other models that are more efficient that can run like on phones. They're a little bit more limited, but like the big AI models, they consume a lot of power. And Microsoft and OpenAI and Meta, Facebook, they're all pushing now for new nuclear power plants to be opened to simply supply the energy needs just for generative AI. So that's why your electricity is going up. So stop using chat. Oh, no. Use it. Eat us up is a big, you know, but yeah, we have a supply problem now. Until about 5 years ago, we had excess, and now we're falling behind the curve. So we need more electrical energy to keep pushing their technology forward, or we just need to go back to clubs and loincloths and give up on the whole thing. Anyway. Well, they're surveyed, but is PG&E going to say no to somebody that wants to buy a lot of power from them? No. Right? So, yeah. Go free market, whatever. Yeah, okay. The free market's a lie. But yeah, all of technology comes with a cost, and it's just a question of the cost. Like I pointed out, great efficiency gains from technology, right? We can become more efficient. But then you get stuff like AI, which is like, oh, let's just use all the power. which is, again, fine. AI improved lives. It does. It also causes life to go, not go so good. But overall, okay, I'm going to be an old man, and I'm going to be your dad for just a second. Why do we fight? Why do we fight wars? Why do we fight each other? Resource. The answer is always resource. It can change from the kind of resource, right? In our modern day, it tends to be over money or property. Back in the day, it was over, I killed the mammoth before you did, right? Like it was always a resource, right? But what's another word for resource? Energy. It is always a fight over energy in whatever form it takes, okay? So how do you solve the world's problems? Provide more energy. Because if there's enough energy and people are getting enough supply, then you have places in Africa and India that aren't connected to the electrical grid that suddenly have electricity that can purify their water, get an X-ray machine, be able to treat them for something, right? And the discrepancies start to not be as stark, right? Energy is the great equalizer, okay? And so my fatherly advice to you is go out and figure out how to solve the energy problem. Whatever form that takes, right? In your chosen fields, it's really going to come down to resources, and that resource is going to be energy in some form. And so the more we can do to produce energy safely, cleanly, the better off our environment will be. And I think the more the wealth will be spread around. We're always fighting over energy in some form. So go fusion. All right, what were we doing? Oh, vacuum cleaners. Speaking of energy. Can we find the resistance of this vacuum cleaner? Yeah. We got voltage and we've got current, don't we? What's the relationship between voltage, current, and resistance? This one just goes straight. Just meditate on it for a second. What do you say what's the stereotypical meditation sound? Ohm. So Ohm's law. You guys laughed at that one and you didn't laugh at Ohm on the... Oh, geez. Fine. All right. So the resistance is going to be voltage divided by the current. The voltage is 120. The current is 12. Even I can do that one. Since it's all in SI units, what is the unit going to come out to be? It's going to come out to be ohms. Is 120 divided by 12 10? Sure. Okay. I said I could do it, and then I freaked out. Okay. How much power does it use? It's current times voltage, isn't it? Or current squared times resistance, or voltage squared divided by, pick your poison, right? Current is, was it 120? No, current is 12. Voltage 120. That looks like 1440 to me. Right? Was that hard? No. Okay. You can see here how we've like abruptly gone from vectors and fields and pictures all of a sudden to like kindergarten levels of algebra, right? Okay. So that's kind of what happens in physics 2B with electricity and magnetism. It starts off really hard. We're grappling with these esoteric concepts and things, and then all of a sudden, boom, it becomes real and somewhat straightforward, right? Okay, so let's tackle one that might be just a little bit more involved, just a little bit, right? Not so bad, but just a little bit more involved. And then, of course, by Thursday, what day is it today? Tuesday. By Thursday, it's going to get a little bit hard again, right? But it's not like Coulomb's law and vector hard. It's going to be more hard in the sense of keeping track of everything. So circuits, as we move into more complicated circuits, we got to keep track of more things. Okay, 100-watt light bulb, 8 hours a day for 1 month. So we want to know the total cost. This kind of problem is really like a chapter 1 conversion problem. okay? Because you're just kind of going between units and different things. So we know that the cost is 14 cents per kilowatt hour. $0.14 for every kilowatt times hour that is consumed, right? That's our cost. So if we're going to find the total cost, like what are we going to multiply by to get dollars here? Yeah, we need to cancel the kilowatt hours, don't we? Right? We want to come in here and say, wah, wah, right? So that we can end up with dollars. So we need to find the total number of kilowatt hours that this light bulb has consumed in 1 month. So how do we find that? Well, what's a kilowatt hour? Kind of a stupid question. It's a kilowatt times the time, right? So let's first find the kilowatts for this 100 watt light bulb. How many kilowatts is that? We already did this. 0.1 kilowatts, isn't it? Okay. So now what time are we gonna multiply by in order to get kilowatts times hours? It's not 8, because it's 8 hours a day. But then it ran for 1 month. Right? So we've got to find the total number of hours there, right? So if it's 8 hours for every day, how many days are there in 1 month? About 30, right? Okay. So 8 times 3 is 24. So 240 hours, right? So we're going to multiply by 240 hours. That's like the total number of hours if the bulb runs for 8 hours a day for a month. Let's see, is that 24? 24 kilowatt times hours. And so I come back over here and I shove that in here. 24, no, wrong side, Mr. Balogh. Shove that in here. 24. So whatever 14 times 24 is, I got $3.36. Doesn't sound too bad, does it? 3 or 4 bucks for 14 cents a kilowatt hour, which is kind of the national average across the United States right now. It's edging up. But that's just one bulb for 8 hours. Do you have a light bulb in your house that's on for 8 hours a day? Probably longer, right? Okay, right, okay. Those late night study sessions, right? So you're like, but I have LED bulbs, Mr. Balogh. So you are amazing, right? Which means you're running at like 10, so you're like at 33 cents, right, for the month for a LED bulb because they're so much more efficient, right? Okay. But you add it all up, right? And it could be, but this isn't all they charge you for. I didn't have time to go into it, but your electrical bill has a lot of other charges on it for things like distribution, transmission of the electrical energy, right? So, and all these different surcharges and making people feel good about nuclear decommissioning and a bunch of other things, okay? No, it's just better to not use electricity when you don't need to. I'm gonna be your dad again. Turn off the lights! Like, seriously, if you walk out of a room and there's nobody, heck, if there's somebody in it, turn off the light. Okay? Because if the light's on and there's nothing going on in that room, the electrons are being used. We don't want to use them. We don't want to keep them. Right? Why? So here's an experiment for you to try. Okay? Go home tonight. Okay? And before you go to bed or whatever, in your room, living room, right, whatever space is yours, right? Turn off the lights and then just look and see how many LEDs are still glowing on devices around you. Okay? Did you know that a PS5 that is sleeping is using the same amount of energy as when you're gaming? Most sleep modes, well, that's not fair. The PS5 actually improved this just a little bit. It's the PS4 that was really bad. PS5, I think, cuts it down to 30% of the load while gaming, right? But they're not, when you put things to sleep, they're not really asleep. And this is called an electricity vampire. Okay? You have your TV, you have your computer, you have your laptop. Something is like asleep, but a sleep mode just means it's ready to turn on the instant you wiggle the mouse or do whatever, right? It's not really off. It's still drawing electrical energy. And if you run those 24 hours a day, just in sleep mode, right? 24 hours a day, 7 days a week, you're not at home right now. How many devices right now at home are asleep instead of off? Right? You can cut your electrical bill fairly significantly by putting in kill switches. My children just hated this because at night I would go up and I'd hit the switch that was connected to the Wii and the satellite TV and like all that. Because at night we're not using it. So I just clunk one of those outlet strips of the switch, punk, they all shut down. Dad, I got up in the morning. It took me 3 seconds extra to turn on the Wii. Right? Yeah, it's going to take, yeah. So come home, turn on your computer, walk away, get something to eat, right? Come back, right? Like it doesn't need to be sucking up the electricity while you're just effectively not using it. So many of these things that are like, oh, that's really nice to do, they just suck electricity, right? So look for ways to become more efficient in electrical energy usage and you end up paying less money because everything comes down to energy. I will see you on Thursday.